Okay, here we go. Unit 5, Lesson 2. Let's find an athlete for you. Yeah, this one will work. Steph Curry's dad, Del Curry. He was a great shooter. It looks like he was on the Cavs. Did not know that. He also played for the Hornets, and he was lights out as a three-point shooter. No surprise, Steph is the best shooter in the world. His dad was one of the best shooters before him. So, anyway, Del Curry. All right, here we go. Select all figures for which there exists a direction such that all cross sections taken at that direction are congruent. Wow, tough problem. Okay, no big deal. So you want to draw like a triangular pyramid for A. So let's do that. Triangular pyramid means it's a pyramid with a base that is a triangle that has an apex to each vertex. So this is a triangular pyramid. There exists a direction such that all cross sections taken at that direction are congruent. This would never happen because if I took a vertical cross section of like this one, so we cut this, imagine you had Play-Doh in the shape of a triangular pyramid. We did a vertical cross section, you'd have this cross section would be different from this, as would a horizontal. Like you'd have a much smaller cross section. So like this one would not be congruent, same size and shape as this. So triangular pyramid's a no-go. Now let's look at square pyramid. So square pyramid. Base is a square. Cross section. So this cross section would be like a tiny square versus this. So that those would not be congruent. Vertical over here would not be congruent to this. So that's out. Rectangular prism. Here's a good example, like the Jenga tower. This is a rectangular prism. This one, now we're talking. So if you took a horizontal cross section, you would have the same congruent shape top as this, as is this. So that one would work. All right, cube, here we go. Cube is a square, like the Rubik's Cube. That's another one that would work. I'll tell you why. If we took a horizontal cross section, here's a good example. This horizontal cross section would be the same congruent, same size, same shape as this. So these two would be congruent. So cube would work. Now let's look at the cone. Cone. Okay, let's think. If we did a horizontal cross section, this would not be congruent to this. And if we did a vertical cross section, you'd have a larger triangle than that. So cone's out. Cylinder might have a chance. Let's look at the horizontal cross section. So you got the base right here. If we did another horizontal cross section of this cylinder, all three of these, 1, 2, and 3, would be congruent. So cones, cylinder is good. And then sphere. Sphere is tricky. Let's see. All cross sections at that directions are congruent. Well, let's look at the halfway up. So say we chop this sphere in half, like right in the middle. Is that circle congruent to this? No, this one's bigger than that. So I'm going to say C, D, and F. And then I'm going to move on because that's the best I could do. All right, number 2, draw the cone. Imagine an upright cone. That upright cone, it just means that it's not tilted. So this one is upright. Here's an example of an oblique. So we're not talking about oblique cones, we're talking about upright. Okay, imagine an upright cone with its base resting on your horizontal desk. Sketch the cross section formed by intersecting each plane with the cone. Vertical plane not passing through the cone's most top point. So here's a vertical plane. It's we have to sketch the cross section. So it's going to be a triangle, but it's not going to be as big as this cone, as the through the middle. So it's a little bit smaller triangle than the one that goes through the middle. Okay, horizontal plane. You chop this cone in half, you're going to see a circle, because the base of a cone is a circle, but it's going to be half, or it's going to be less than the base. So if this is the base, any horizontal cross section is going to be a result in a smaller circle. Does that make sense? So it's going to be a circle, not as big as the base. Okay, and then a diagonal plane. You're going to learn about this once we get into the Play-Doh. It's actually an oval. And number 3, name 2 figures for which a circle can be a cross section. How about a sphere and a cone? All right, 1, 2, 3 down. Number 4, sketch the solid of rotation formed by rotating the given 2-dimensional figure using the dashed vertical line as a cross section, or as an axis of rotation. So what you want to do on this is just trace this line real quick. And then also trace this. Now, if you don't have patty paper, you can still do this problem, so don't quit if you don't have patty paper. But what you can do is just, when I flip it, make sure the line lines up. Right there. And then, hang on, almost there, right there. And then just use your compass. I'll show you how to do that. It's not perfect, by the way. Hang on. If you use your tracing paper, this makes it easy. Now I'm just going to put little points along this line, and then I'll fill in the line later. Does it have to be perfect on your homework? No, but if you are doing this in the real world, for sure. Okay, so I got my lines that I want to connect, so my dots. Now you can try to hand draw this too. That's an option. But patty paper will really help you. Now we need to get the solid of rotation, so we're going to connect right here. And then you might even draw yourself like a base, like so. Anyway, there you go. And this whole thing is the solid of rotation. The axis of rotation is right here. Is the axis of rotation. Okay, number 5. Draw a 2-dimensional figure that could be rotated using a vertical axis of rotation to give the cone shown. So look back on problem 3, unit 5, lesson 1. So this should work right here. Let me just make sure it's parallel. there. Okay. So this 2D shape would result in the cone. Imagine you're building like chess pieces. Anyways, if you use this axis of rotation to rotate, so this is your pencil, which you're going to see coming up. So when we're in class, we're going to do this pencil rotation, and then we have like a piece of cardboard right here. So you rotate this shape right here with this axis of rotation. This is how I do it in class. It'll eventually create a cone. All right, that was number 5. Number 6, regular hexagon and regular octagon, both inscribed in the same circle. Which of these statements is true? Okay. My advice is do both constructions and then find the perimeter. So I use this blank sheet of paper right here. So we'll use the same size radius. So there we go. Create a circle, same radius, so we just move the compass. We're comparing regular hexagon, regular octagon. Okay, hexagon or octagon's easy, just go top. Through the center, here's one, and then go over here to here, and then 45 is like halfway. Okay, now let's go quick so I don't waste all your time. This is how I would do it. I would actually build them and then think about what they're asking. Okay, there's the octagon. Now the hexagon, it's pretty easy. There's 2 of the points. I haven't changed my compass, so all you need is that. There's one right there. And one more right here. Showing you how to quickly build these things so that you can work with it. Okay, so now we have regular hexagon inscribed in a circle. They all have the same radius. Okay, now gotta answer some questions. The perimeter of the hexagon is less than the perimeter of the octagon, and each perimeter is less than the circumference of the circle. Okay. Huh. Is it 6-sided? Is it 8-sided? Okay. So let's just measure what our radius was. Let's see if I got lucky. No, not quite. Okay, so let's call these 2.85. Okay. So this is, we'll just call this 2.9. And that means this is also 2.9. Okay, we're on to something. So each of these radii is 2.9. Now with the hexagon, I know for a fact this is 2.9. I know this is 60, because 360 divided by 60 divided by 6 is 60. That means this and this are the same, meaning these are both 60, because the difference is 120, so this is 2.9 also. So 2.9, 2.9, 2.9. So let's see, perimeter of this is 2.9 times 6, which equals 2.9 times 6, 17.4. This one's tricky. All right, 2.9, this is 2.9. This is 360 divided by 8, which is 45. These two are the same. So 180 minus 45, 135 divided by 2. These are each 67.5. Okay, let's draw an auxiliary line. This is the height. We gotta figure out what is this right here. So 67.5 versus 22.5. So this is adjacent, opposite, hypo. So I'm going to use the hypo to solve for the adjacent. So we're going to say cosine 67.5 equals 80j over hypo. Just talking through my thinking here. Cos 67.5 is 0.383 equals adjacent. We don't know yet, so we'll just call it x over hypo, which is 2.9. So we just cross multiply 2.9 times 0.383 equals x times 2.9. 1.1. So x is 1.1. So this is 1.1. This is 1.1. That means this is 2.2. So perimeter is 2.2 times 8, which equals 2.2 times 8 is 17.6 versus 17.4. Okay, so we got the perimeter. Perimeter of the hexagon is less than the perimeter of the octagon. Yes, just barely. Each perimeter is less than the circumference of the circle. Circumference represents the distance around the circle. It's kind of like perimeter of a circle. Yes, that's true. They said which, so I believe A is the winner. The perimeter of the octagon is less than the perimeter of the hexagon. No, that's false automatically. The perimeter of the hexagon is greater than the perimeter of the octagon. No. I already know this is better, or the octagon's bigger than the hexagon. So that's a no. Perimeter of the octagon is greater than the perimeter of the hexagon. Yes, that's true. And each perimeter is greater than the circumference of the circle. No way. The circumference of the circle is going to be greater than both of these. And I'll show you why. Circumference is 2 pi r. So 2 pi times 2.9. So 2 times pi times 2.9, 18.22. So yeah, cool. It's A for sure. Okay, 7, tough problem. I already did it for you, but that's okay. I'll do it again. So you got a rectangle. This is 10. Find the perimeter. Ooh, perimeter. Last one we had to do area. Okay. Okay. That means we need this, and we need this. And we're gonna use this 10 to find y. So color, label, right, choose, tan 70 equals op adjacent. So tan 70, 2.747 equals 10 over y. Y 2.747 equals 10. 10 divided by 2.747 is 3.64. Y equals 3.64. So this is 3.64. Now to find x, we're going to use Pythagorean. So a squared plus b squared equals c squared. So 10 squared plus 3.64 squared equals x squared, right? X. So 100 plus 13.25 equals x squared. So 113.25 equals x squared. So the second x squared, 113.25 is 10.64. Square root both sides, x equals 10.64. So this is 10.64. Now you need the perimeter, which is this, 10.64, plus this, which is 8, plus this, which is 10, plus this, which is 8, and don't forget about y, 3.64. So that will all equal the perimeter. So you just add them all up, pretty easy. So 10.64 plus 8 plus 10 plus 8 plus 3.64, 40.28. So we'll just call it 40.3. Done and done. Tough problem. All right, that was Unit 5, Lesson 2. Keep trying.